Hi everyone. Today we'll begin talking about one specific star, a star being our star, the sun. So by the end of this week in this lecture, this module, we will be able to label and also describe the different layers of the sun's atmosphere, as well as explain the way that we see the sun's surface, including sunspots and their cycling, the sun's magnetic field, and solar flares. So let's do a quick review of the types of spectra that we can see, that we do see and measure. A continuous spectra is where we are getting all wavelengths of light from an object. So we're seeing the full visible wavelength range. When we're looking at a continuous spectra through a cloud of gas, we're going to see a spectra where that cloud of gas is absorbing certain wavelengths. So we can use this continuous spectra with the dark absorption lines to tell us what kind of gas we are looking at. What kind of gas we are seeing that light travel through, I should say. And if you look at the spectra of the gas itself, we will see that it is sort of the opposite of the absorption spectra. We see the emission spectra, so what wavelengths that gas is absorbing and emitting. So we can use this to tell us quite a bit about different gases that are present in different stars, including in our star. So for example, here we have a continuous spectrum. If we were looking at an object that was emitting a continuous spectrum and it was traveling through a cloud of hydrogen gas, the spectra we would see would be this continuous spectra with the hydrogen absorption lines blacked out, because the hydrogen would be absorbing these wavelengths. So what we would end up receiving or viewing is this spectra with the hydrogen characteristics removed. We can also see this information in a graph. So in the same way that we can see on the emission and absorption spectras, the rainbow bar, we can also see this information in terms of a graph. So where you see a dip in the intensity, that is corresponding to the wavelength that is no longer present because the gas that this light traveled through absorbed that specific wavelength. And remember that we can measure the velocity of an object in space in terms of how it is moving towards or away from Earth by using the Doppler effect and the Doppler shift. When we have a star that is moving towards Earth, we will see its emission spectra shifted towards the blue. When the object is moving away from Earth, we can see that emission spectra is shifted towards the red. So by measuring over time, we can see the pattern of red shift, back to neutral, back to blue shift, back to neutral, back to red shift, and we can actually measure how things are moving relative to the Earth. So here's the diagram, for example. As this object is moving away from Earth, it's red shifted. As it's moving closer to Earth, it is blue shifted. Here's another diagram that shows as this UFO, which is fake, it's a cartoon, is moving towards the Earth. We'll see that the light it is emitting towards Earth is blue shifted. You see blue here. Whereas something that it is moving away from, say this star here, as the UFO is moving away from this star, it is seeing red shift. As the UFO reaches Earth, grabs a cow, and leaves, we will now see the light from that UFO being red shifted if we're sitting on Earth, because that object is moving away from us on Earth. So let's think about the sun, my favorite star. The sun is quite large. It is about 109 times the size of our Earth. And if we look at all of the mass in our solar system, the sun, the planets, all the asteroids, the sun actually makes up almost all of it. So 99.86% of all of the mass in our solar system is the sun. Very big compared to our solar system. It consists of hydrogen and helium for the most part. It is a very average star, and it's about 4.6 billion years old. So the brightness of our sun is a negative 26.74. Remember that the higher, the more negative the number, the brighter the star. The larger the positive number, let's say if it was a 10, that would be very, very faint. We wouldn't be able to see it with the eye. And the angular size of our sun, so if you look up in the sky, how much of the sky does that sun take up in terms of angular diameter, is about half a degree, so 31.5 arc minutes. So that's a little more than half of a degree. So if we look at the breakdown of what the sun is made of, we see it as mostly hydrogen, about a quarter helium, and then other things in very, very small amounts. So everything else is very small amount. So the composition of our sun, we determined that by using spectra, but it wasn't until a scientist named Cecilia Payne in 1925 figured out how to calculate how much of each element were present, did we know the percentages of what was present on Earth, in the sun. So previous to this, using the spectra, we were able to determine, yes, there's hydrogen, yes, there's helium, but we didn't know the proportions. So this woman, scientist here, invented the way to calculate how much of each element was present. She also proved that elements might still be there, even if we don't see their spectral lines. So even if the spectral lines are not detected, that doesn't mean that the element isn't there. It might be not the ideal temperature for that element, might be difference in density, or that element is not at visible levels. So she was able to say the sun is about 90% hydrogen, the rest is helium, anything else is in really teeny tiny amounts. She was pretty accurate in that most of the sun is hydrogen, the rest is helium, and everything else is pretty much everything else, but it's more like 75% hydrogen, 25% helium. It did, however, take decades for her work to be accepted and used and shared. So when we think about the sun, we think about the three different layers of the sun's atmosphere. So there's the photosphere, which is the surface of the sun. So that is the visible layer, here, orangey. Most of the light from the sun comes from this layer. It's about 400 kilometers thick and almost 6,000 degrees Celsius. If we then move up or outwards, up sort of into the sky off the surface of the sun, we would be in the chromosphere. So the chromosphere is mostly helium, and it looks reddish pink. It's this part. It's a lot thicker. It's 2,500 kilometers thick, and it is a lot hotter. It gets up to about 30,000 degrees Celsius. And the most outer layer of the sun's atmosphere we call the corona. So the corona is only visible during an eclipse. We can't see it any other time because the photosphere is way too bright. But it is millions of kilometers thick. So the corona extends very, very, very far out from the surface of the sun, and it's between 1 and 2 million degrees Celsius. Very, very hot. So you'll notice that the temperature increases with distance away from the sun. So here's another diagram. We see the surface of the sun is the photosphere. Then we have the pink, much thicker layer, which is the chromosphere, and then the corona. So this is a solar eclipse here, a total solar eclipse. And we can see this very thick corona, but it's only something that we can view during an eclipse. It is not bright enough to stand out compared to the photosphere and even the chromosphere on a regular day. So the photosphere, surface of the sun, very, very hot. It is glowing. It's very bright. It's the visible surface of the Earth. It's actually quite a thin layer, and it's very, very low density gas. So if you were to think of the sun as a bowling ball, so if you were to shrink the sun down to a bowling ball and create the photosphere to scale, it would be about the thickness of a piece of tissue paper. So a tissue on top of a bowling ball, that's about how thick this layer is. Very low density gas, very, very, very thin. The photosphere has sunspots, which we'll get into a bit later, that appear and disappear throughout the year. They move around on the surface, they appear, they disappear. So the elements in the photosphere, we're able to determine what the photosphere is made of using the sun's absorption spectrum, of course. So the deeper layers of the photosphere, more towards the center of the Earth, center of the sun, we assume to be black body spectrum. The higher layers, however, towards the outermost portion, absorb certain wavelengths when the electrons are jumping orbits. So we can actually tell exactly what the photosphere is made of using the sun's absorption spectrum. So there's the two yellow lines very close to each other. That means sodium is present. We can see that hydrogen is present, magnesium is present, calcium, iron. Those giant sunglasses, if you're thinking of the cartoon version of the sun with the sunglasses, we're able to use this absorption spectrum to tell us what is present. And the sun increases temperature with depth. So if we're thinking about the sun itself and not the atmosphere, it increases in temperature with depth. So the sun is warmest in the center, and it is less warm at the surface. So the photosphere is very, very affected by the fact that the center of the sun is incredibly hot. So it's sort of like boiling water. Our photosphere is experiencing convection the same way that a pot of boiling water would. So the center of the sun, remember, is very, very hot. The temperature of the sun increases with depth. So as you get closer to the center of the sun, it's going to get hotter and hotter and hotter. So for the photosphere on the surface of the sun, it has all that heat beneath it. So what this causes is convection, where we have warm material rising until it gets to the surface of the photosphere, where it's able to cool down a bit. That cool material will sink, warm up again, rise, cool down, and sink. We have this convection effect. So what that causes is what we call granules. So this is the most detailed photo of the surface of the sun that exists. It was published about a year ago. And this is what the surface of the sun looks like due to this convection effect. So it's sort of darker edged regions with brighter areas in the center. So if we look at this cartoon version here, we see the darker edges sort of outline what we call each granule. So the center, the brighter color, is really hundreds of degrees warmer than the edges are. And that's because where we have that rising, very, very hot material is in the center of the granule. That hot material then reaches the surface, starts to cool down at the edge of the granule. Once it gets down closer to the base of the photosphere, it's going to heat up again and rise up through the center of the granule. So the granules are constantly moving. They're not set in space because remember, we're not talking about solid. We're talking about all gases here. So the granules last about 10 to 20 minutes before they fade and shrink and then are replaced by a new granule. So this is a snapshot, but if we were able to look at this in real time, it would be constantly moving around. So the granules really only last for about 10 to 20 minutes before a new granule comes in and takes its place. So they will start to shrink and fade, and then another granule comes in. So we know that the center of the granules are rising and the edges are sinking very quickly, about 900 miles per hour. And we know that because the centers are warmer, the edges are cooler. So we know that that center material is rising up from the base, the warm base of the photosphere. The cool material is going to be sinking down. However, we can also measure this using the Doppler effect. So we're actually able to see the red and blue shifts on the surface of the sun that show us that we have motion towards the Earth and motion away from the Earth, all very close together on the surface of the sun. So above the photosphere, we have the chromosphere. So this is the pink layer. Very, very hot, about 30,000 degrees. It can be up to 30,000 degrees, and it's much thicker than the photosphere. So it's the layer of the atmosphere directly above the surface, and if you look at this picture of the solar eclipse, where you see that pink light, that is the chromosphere. Then we have the corona further outwards. And there isn't a very clear defining line between the chromosphere and the corona. The chromosphere just sort of slowly blends into the corona. It's about 1,000 times fainter than the photosphere. So if you look up at the sun, if you see a picture of the sun, we don't normally see that it's surrounded in pink. That's because it's not quite bright enough to show that pink all the time. We can't always see that chromosphere. But during an eclipse, we often can. If we remove a lot of the light from the photosphere, we're able to see these other two layers, especially that chromosphere, that really nice pink layer. So why is it pink? That is because it is mostly hydrogen. So the emission lines of hydrogen are red, blue, and violet. So when we see excited hydrogen, we see the color pink. It emits wavelength in the color pink, or it emits a wavelength combination that to us looks pink. So when we are seeing that chromosphere, we are seeing those excited hydrogen atoms. We are seeing that pink color. So here is a temperature chart. So if we're looking at here, the height above the photosphere. So if we're looking at 0 as the surface of the sun, the photosphere there, and then we're moving upwards or outwards away from the surface of the sun, out towards space, we have the photosphere, and then we move through that chromosphere out towards the corona. So we think of that in terms of temperature. We see the surface of the Earth, the surface of the sun, quite hot. As we move up to the chromosphere, we actually hit about 10,000 Kelvin, and then a very quick and steep change to almost 1,000,000 degrees, or almost 1,000,000 Kelvin as we move out towards the corona. So in the chromosphere is where we have that very high transition, or very large transition in temperature out towards the corona. So in the chromosphere, almost all the gases are transparent. There's only a few very specific wavelengths that are absorbed. Any photons that are emitted from these wavelengths are high up in the chromosphere. So how do we actually see and measure and learn about the chromosphere? We have what is called a filtergram. So it is a way to image the sun using light at specific wavelengths. So we can look at the specific wavelengths that we know are absorbed and emitted from the chromosphere and image just that. So it's usually very far UV or X-ray images that we can actually look at the chromosphere. So we're looking at the specific wavelengths that we know are emitted from the chromosphere, which is always very short wavelengths, very high energy. So in the chromosphere, we sometimes have these upward jets of gas. So we will have very tall jets of gas that extend almost straight upwards into the atmosphere of the sun. And they last about 10 minutes, so they're very short-lived, but it's a bit like a small explosion where it's a huge jet of gas extending upwards, about 10 minutes, maybe at the longest. And it is really cooler gas from lower in the chromosphere extending upwards into the hottest area of the chromosphere is why we are able to see them. This generally appears, we'll see these around the edge of supergranules, which are very extra large granules. So when a granule becomes extra large, you're going to have extra activity around the edges. So we sometimes see these jets of gas extending upwards all the way up to and into the chromosphere. That is generally around these extra large granules where we have a lot of activity. So moving upwards from the chromosphere, we have what is called the corona. So the corona is the hardest to see. It is the outer layer of the sun's atmosphere, but it almost doesn't end. It's huge. We say it's millions of kilometers thick. But the corona, it's more like it just fades out. So it's not as if there's a clear barrier and, okay, this is the end of the sun's atmosphere. Here's the edge of the corona. It's more like it just fades out with distance from the sun. Only visible during the eclipse and incredibly warm. So here is a picture of an eclipse where we can see that corona. So it's the outermost portion of the sun's atmosphere, very, 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 very thick. And it's a very low density layer of ionized gases. So we use what we call a coronagraph to observe the corona. It's it's a telescope that actually blocks out the photosphere so that we can see the corona around the photosphere. So the corona itself, in terms of thickness, is actually over 10 times the diameter of the sun. We know it reaches about 10% to the distance of the Earth. So it's very, very, very thick. And it, like I said, it sort of fades out with distance. So there's not a clear boundary. Here is the corona, here is not the corona. It's more like it just fades out. So we can look at the spectrum of the corona itself, and it tells us that the temperature is actually rising with height. So the heat in the sun's atmosphere comes from motion of the magnetic field. So the fact that the magnetic field of the sun, which we'll get into later in more detail, the fact that it is moving around allows gases to flow outward away from the sun, bringing heat away from the sun and into the outer atmosphere of the sun. So I said the corona sort of fades out to the point where it is not quite thick enough to be called the corona anymore. But there's actually gases that can move, or I should say atoms, not gases. There's atoms that can actually leave the surface of the sun, move up through the atmosphere, move out through the corona, and then continue traveling outwards into space, leaving the sun completely. This is what we call solar wind, sort of an extension of the corona. And it's mostly caused by magnetic fields, the magnetic field of the sun, and where that magnetic field leads outwards to space. So a lot of the magnetic field of the sun is leading outwards. So this allows gases and atoms to actually flow away from the sun, leaving the sun, and flowing out into our solar system. So this is what we call solar wind. So these atoms and these gases can actually reach Earth and move much further than Earth. When they travel past Earth, they're usually moving between 300 and 800 kilometers a second. So what this means is the sun is slowly losing mass. Atoms are slowly, or quickly, but not in mass amounts, moving away from the sun, following these magnetic field lines. These atoms are flowing outwards into space. The sun is very slowly losing these atoms. It's losing this mass as what we call solar wind. So the sun's atmosphere, we have our photosphere at the surface, and then we have our pink chromosphere, and then we have the very thick corona. The sun is very, very similar to almost all other stars. It is very, very average in terms of a star.